So, good, I'm recording. Okay. So, D'Alembert solution you can apply to both when you have initial conditions on the full real line. Okay. And when we have the quarter plane, okay, have to use a method of extension, essentially, where we use the general form of the solution using the boundary condition. Okay. And I worked through an example of this in the recorded lecture on Friday. Well, yeah, that I recorded for Friday, I guess. And we also talked about an example in the in-person recitation that we went over. So there are some methods then for finding solutions, essentially, that rely on identifying the fact that solutions should be some linear superposition of drifting, some sort of drifting function that moves along the rightward and the leftward characteristics of your space, right? So this would be a typical rightward moving characteristic, x minus ct equals s, and this would be a leftward moving characteristic, x plus ct equals some other s. So I could call this like s2 and s1 or something like that. And that can essentially carry you a long way through solving sort of different forms of initial value problems, as we've seen. So the main way of establishing existence that we've talked about is typically just constructing solutions. One caveat is that for classical solutions, okay, we need continuity, okay, across any region boundaries. I'll say region boundaries, okay. And so what does this mean? So if I have the quarter plane problem, okay, and I know that, as I've discussed before, I know that I have a certain solution in this region, basically above the line x equals ct, and I have another solution down here below the line x equals ct, then these limits essentially have to match. So I have to match basically u, ux, ut, uxx, and utt at those boundaries, okay? At this boundary here. And just like in the case of the transport equation, we can do that by just writing out the solution and then taking that limit and imposing that condition. And the result is that you're going to get some condition on the function that defines your boundary condition, h of t, and then your typical initial conditions, which we've called, phi or psi or something like that. Okay. So sorry about those noises. I keep getting calendar reminders that I can't turn off. Okay, so that's existence for the wave equation. And today we're going to mostly focus on the problem of uniqueness, okay? And then we'll talk a little bit about the effects of inhomogeneities on the wave equation. We have some form of forcing. So the technique that we're going to talk about with respect to proving uniqueness for the wave equation is relevant here and also to the heat equation, also to Laplace and Poisson equation. The general idea is that you construct something called a functional, which just means it takes as an argument a function, and then it outputs essentially a scalar, usually. And you know, these are, if you're taking the analysis course, you'll see this in functional analysis a lot. And the motivation for using them here really is that it is, in the case of a wave equation, actually the sum of physical energy that you would get from the wave that you have. The combination of potential and kinetic energy, and knowing that you have conservation of energy means that you can say something about the evolution of the solution. You can then also use that form of energy functional in order to prove things about the uniqueness of solutions, okay? So what's the definition of this energy? Well, if we assume that U of xt, okay, is a smooth solution to this PDE, I'm gonna write it down below where I have more room. To this PDE, right? So we have our standard wave equation, and it's just going to be on the half plane. So I have x is in r, and t is greater than 0. And my initial conditions are going to be the position of the, or the displacement, the initial displacement of my string, for instance, and my initial velocity, okay? And so these together form our initial value problem, okay? This is our IVP. And we'll assume that if I have the solution, then its time derivative and its spatial derivative are L2 integrable for t greater than 0. So I'm going to be able to take an integral, okay? Then, okay, you see I have not left myself enough space on the slide, okay? Then I can define something called the total energy of my wave solution, which has several specific properties that I'll discuss, okay? So let me just advance the slide, okay? So I'll just rewrite the definition so that this is all on the same slide. So assume, okay, U solves the wave initial value problem, right? I won't rewrite that. And ut ux or L2, just rewriting what I had on the previous slide for t is greater than or equal to 0. Okay, then the total energy is defined as E of t is equal to the integral from minus infinity to infinity of 1/2 u sub t squared plus c squared over 2 u sub x squared, okay, integrated with respect to x, is finite, okay? Why is it finite? Okay, well, it's trivially so because I already said that ut and ux are L2 integrable. Okay, so because of the linearity of the integral, I know that each of the pieces are finite, so I can sum them up and that thing's finite. Okay, but I want to break this down into two pieces, right? So here I have what I would call the kinetic energy, okay? And here, this integrated part here, this is my potential energy, okay? And sometimes I call this K of T, right? And I might call this capital P of T, okay? And kinetic energy is going to be essentially due to the velocity, okay, the movement of the string, okay? So it depends on the velocity of the string. It depends on ut, okay? So ut here, remember that's our velocity, okay? And so we think of this essentially as something like the mass of the string divided by 2 multiplied by the velocity squared, okay? 1/2 mv squared is going to be our kinetic energy, just like sort of the standard definition of physics, okay? We've non-dimensionalized things in the derivation of the string so that the string's sort of mass locally is 1, okay? The potential energy here, this essentially is the energy stored in the string due to tension, okay? So remember, tension depends on the deformation gradient. We approximated that by saying, well, it essentially is going to depend linearly on the deformation gradient, okay? So this essentially is the stored up energy that you get by applying tension to the string, okay? So this represents the two contributions to the energy of the string. Whatever energy is currently represented by the motion, and whatever is represented by the tension, okay? And so in order to prove that this energy is conserved, that whatever energy is stored up as tension gets converted into kinetic energy, we can show that this quantity is going to stay constant, okay? So in order to prove conservation energy, what do we need to show? We just need to show that E of t is going to be constant for all time. And we can use the PDE itself to do that, okay? So just like you'd expect for, you know, any conservative physical system, okay, if I capture all of the contributions to energy, they should always sum to a constant, okay, or their time derivative should be 0, okay? So the point that we're going to show is that E of t is conserved, okay? In other words, this is our conservation of energy, okay? So essentially, to show this, all I need to do is multiply the PDE that I started with by U sub t and integrate, okay? So what PDE did I start with? I'll just very quickly flash back to here. Remember, here's my good old wave equation, okay? So I just take U sub t is equal to c squared u sub xx, okay? I multiply both sides by u sub t, okay? And then I'm going to integrate. All right. I need to slip in my dx there. Okay. So once I do that, okay, I can evaluate it as follows, right? First of all, I know that this quantity here, ut times utt, okay, I can rewrite that as the partial with respect to t of ut squared over 2 dx, okay? So essentially, I've just taken this quantity and turned it into something that looks more like what I have in the functional that I'm trying to capture with this, okay? On the right-hand side, okay, I could do integration by parts, okay? So if I integrate up with respect to x this, and then I differentiate this with respect to x, then I get the boundary terms, c squared, ux, ut, evaluated between minus infinity and infinity, okay, in the x direction. Subtract from that c squared, the integral from minus infinity to infinity of ux, uxt dx, okay? Just again, the result of integration by parts, okay? Now, this term could be problematic if I don't have a solution that's compactly supported, okay? So essentially at this point, I need an additional condition, okay? And that's essentially that U has compact support, okay? Otherwise, I have this additional constant floating around, okay?
Since we know they're in L2, doesn't that tell us like that the limit has to go to 0 as we go to infinity?
Right, yeah, that's true, yeah. So that is a consequence of them being L2 functions, yeah, right. I forgot that, yeah. So L2 implies that we have, well, not necessarily compact support, but that L2 essentially implies that the limit as x goes to plus or minus infinity of ux is equal to the limit of ut is equal to 0. Yeah, you're right, Sage. Good point. Okay. So, okay, so what that leaves us with over here is that the only thing we have left is just this integral now that came out of our integration by parts, okay? So we're very close to something that looks like what we found for our conservation of energy. We just need to move that term over to the left-hand side, okay? So, so we can write this now as 0 is equal to the derivative with respect to t of the integral from minus infinity to infinity of ut squared over 2. That was just this term that we had before, Okay, now I'm taking this term and moving it over to the other side. So I get plus c squared over 2. And I can rewrite this as just ux squared over 2 differentiated with respect to t, which is going to be out in front here. Okay, so this is all integrated with respect to x. But what is this thing now? This is exactly my energy that I defined up here. So what I've shown now is that the derivative of my energy is 0 for all time. Okay, so this is equal to E prime of t. Okay, or in other words, that my energy is constant. Okay, so so what I have then is a statement of conservation of energy. I'm going to advance the slide. Can I advance the slide? Okay. So this implies that E of t is constant. Okay. So that means that E of t is just equal to whatever it is at time 0. Okay. Which is given by a half the integral from minus infinity to infinity. Psi of x squared, that's my initial velocity, plus c squared phi prime of x quantity squared. That's my initial spatial gradient, or my initial deformation. And I have t greater than or equal to 0. Okay. So my constant energy of my system is just given to me by this calculation that I can get from my initial conditions. Okay. So this result. Okay. We just needed a couple things to justify it. Okay. So it's justified when, first of all, u sub t and u sub x are integrable, okay, for all t greater than or equal to 0, okay. Also, when they're differentiable, when u is differentiable, for each x and t, okay. And also when there exists an integrable f and g such that u sub tt of xt is bounded by f of x, and u sub xt is bounded by g of x for all xt. Okay. So essentially, when as long as those integrals that we had to do at the intermediate steps of the proof, as long as we can define those. Okay. So so essentially, just that there's some function that bounds them that's integrable. Okay.
That's so we can swap the integral and the derivatives.
Right. Yeah. Yeah. And also, yeah, so that we can even just take those intermediate steps as well. Yeah. Right. All right. So this can be used, as I was saying before, to prove uniqueness of solutions, okay? But the question is how? I haven't told you that yet, okay? And so in order to set this up, okay, let's look at the problem of proving